now is the final section of this chapter. And there's not a whole lot to talk about in this. Let's talk about this nonlinear differential equation, which is a huge subject. So because it's huge, then we don't have too many general formula to talk about, general method. Although there's a lot of specific method, depends on your nonlinearity or the form of the equation and so on. So it's a huge subject. So there's a lot to learn about for nonlinear equations. We actually have a nonlinear dynamics. Have you taken that nonlinear? No one taken. So so you can have a whole course talk about nonlinear equations. Okay, so but for us, we just, I mean, the textbook have two examples, but this is just two examples of many different cases for nonlinear. So for nonlinear ODE, right? In fact, in the beginning, when we talk about 1D ODE and some of the method applied to nonlinear equation, you see that like the separable or exact differential, some of those forms can be nonlinear. You can still solve it easily. And there was a homework problem of the, I call it the potential type, because y double pi equals exponential of y, right? That is also a nonlinear equation. You can solve those. A potential type, you can solve that by first integrate once and get the conservation law, what we call the conservation energy out, right? Yeah, you still have method. Depends on the form of the equation. You have particular method for whatever the form of the equation. There are a whole lot of general ideas. One particular general idea is to avoid it here. And for linear equation, if you have a solution, you find a solution y1 for your whatever your differential operator. If you have a differential equation like that, for linear equation, if you find one solution, then you multiply by any constant. That's also a solution. If you find two solutions, you can add linear combination of that. Then it's still a solution, but all these are not you cannot carry this into nonlinear equation. So that is not the solution. So that might not be zero. Right? You need to be a little bit more careful when doing nonlinear equations. So this is just to avoid a common error. So you have solution for you find one solution, doesn't mean that you can multiply by constant or add to another solution. Okay, so that's one thing. And another general idea of nonlinear equation is that you most likely need to analyze the equation more carefully. I mean, even linear equation, you probably should do that, but for linear equation, because you mostly deal with some particular choice, a particular form of a linear equation that are easy to identify. You already have formula to solve that, so you don't pay too much attention to the form of your equation. But for the linear equation, and in many cases, it's require you to analyze the problem, and especially pay particular attention to the condition, either initial condition or boundary condition, because that would determine the form of the solution. For nonlinear equation, the mathematical form of the solution can change with the boundary condition. So it can change completely. There are some homework problems to show that the different initial condition, then you get the functional form of the solution will be totally different. So that's but one thing to realize that is analyze, look at the equation itself, and then before you do anything, you try to solve it mathematically, whatever method. You just analyze the equation and then see what should happen. So in many cases, if you don't actually know the method to solve it or the actual method to solve it, then you put it on the computer and you integrate that, which is fine. But I mean, any computer method, any algorithm can make error, or numerical method can have different kind of error. You have finite precision error and all that. And so even you get a solution out of a computer program doesn't mean it's actually a solution. So you need to know that whether it's reasonable, the solution reasonable compared with the form that you expected from your the equation. So it's a very simple one. Your textbook used that as one example, but you can use it for another purpose to illustrate that. So a simple equation like y prime is equals to y squared. That is, right. So obviously this is separable. You can integrate that right away. So, but to illustrate what we say talk about is analyzing this equation first. So you can just set the certain x and y coordinate, and at a certain point you set your initial condition is it's first order, so you just need to set your y to a certain value initially or at a certain point. So if this is a 0 axis, you can see that if to analyze that, you just choose different value of y. If y is a positive value, right? Then y squared is positive, which means the derivative is positive. Okay, so derivative is positive. And then so you integrate to a positive x, and it will keep increasing. If y increase, then the derivative also increase, and increase as square. So the derivative will keep increasing, and somewhere along the line, you expect that to go to infinity. It goes to infinity. The question is obviously, it will go to infinity at x goes to infinity, or at some finite time, it will goes to infinity, whatever x prime or whatever. Right. Before you actually solve it, you know that it will go to infinity somewhere along the line, either go to infinity at x will go to infinity, or at a certain finite point. If we had a certain finite point, obviously this solution we call it singular at this point. Right? That is for positive x. And another thing you can do is choose different value. Obviously, if you choose a higher value of higher than your first line, now your derivative actually is higher because y, you choose your initial value is higher, so derivative is higher. As a matter of fact, the derivative only depends on y. You can just say that this derivative is exactly the same as this point. So basically, now you're moving this line to here, right? Basically, you shift the whole line to here, right? Because once you get the same derivative, it will go, right? Also go to infinity. But now, if it go to infinity at a certain finite point, it will not shift to whatever this distance is. It's undetermined yet, but you can shift it a little bit and you get exactly the same. And so now you can see that, but if you choose a smaller one, obviously, now the derivative is is smaller, and how smaller is depends on now. If you integrate back to negative values, and you see that it will go to much smaller one. So now you're saying that if you go to infinity, you delay the point by the same amount, right? So before you do that, you already know a lot of property of the solution. But one thing is fundamentally different if you choose a negative value to start with, right? if y is negative, right? And now the y squared is still is positive. Y is negative. Y squared is still positive. But then when it increase, because y start with a negative value, when it increase, which means the magnitude decrease, right? When the magnitude decrease, say a certain point, then y squared decrease, y prime decrease, the derivative actually decrease at you move up at this point. Start with the negative value, you move up, but then when you move up, y is absolute value is smaller, so y squared is smaller, derivative is smaller, right? Then you go up even slower, and slower. Right? And somewhere along the line, so there's two possibilities. One is it goes to 0 as x goes to infinity. Another possibility, which you because you haven't done the math, so it could cross the line. For this possibility, you now doing some analysis, you rule it out because if you cross this line, y is 0. Y is 0, the derivative is 0. That doesn't make sense. You cannot cross it. If you cross it, then the derivative is non-zero. When it touches the y equals 0 axis, the derivative is 0, so it's flat. Right? So here. You already know that it cannot cross. So you rule that possibility out. So you're pretty sure that it will go to 0 asymptotically as x goes to infinity. Right? So that just illustrates some. So you learn a lot of the solution property of the solution by just looking at and analyzing the equation. For this, of course, analysis is simple. Right? But for even more complicated situation, you analyze that and figure that out, and that could help you solve the differential equation or find a method to solve the differential equation. But this one, obviously, you know how to solve this. This is this dy y squared equals to dx, right? So you integrate that. So that gives you 1 over y, right? 1 over y minus 1 over y, so minus 1 over y. That's the x0. X equals to x minus x0, right? And so you invert that. So this is equals right out. So 1 over y, so which is as a constant, right? And minus 1 over y. Solve it. What is that? It just give you a constant. 1 over y. We'll move it to the other side. So y x will be 1 over this 1 plus x0 minus x. Right. So this x0 obviously is just your the choice of your origin, which in this case doesn't matter because it doesn't depend on x explicitly, just the derivative. You can safely choose it to be 0. Set this to 0, because that is just the initial condition y at 0, right? So you can see that if y at 0, then the solution becomes singular at x equals 1 over y 0. Right, at a certain point, so that what we call the x prime in here. So this point, so if this is your y at 0, you can say that this is y 0, right? And this point, this singular point is this is when x equals this is 1 over y. Right. Right. This equals to that. This is 0. Then the y goes to infinity, right? And now you satisfy what our choice. If y you choose as higher, this one you choose as higher, then this one becomes smaller, right? So it goes to infinity sooner. It chooses to be smaller. Y0 is smaller. This is larger, so it goes to infinity later, right? But then if y sub 0 is actually negative, right? If this is negative, then the denominator is negative, always negative. This is x is positive, start from 0. This is negative. It's always negative, but at x goes to infinity, y goes to 0. Right? So let's satisfy this. So the solution is obviously consistent with the analysis. You just check what once you get the solution, check with all your analysis, see if they match. Okay, so that's one simple example to illustrate this point. I mean, it's pretty abstract still. I mean, even with one example, but if you do that, that will help you to solve a known problem. So, so like in one of my research that I got a solution, I got an ODE. I mean, it's nonlinear ODE, pretty complicated. But what I mean, without writing the form of the equation down here, just the property of this ODE is something like, again, if you use x and y, then just from and analyzing the equation, I found out that if y is too large, then it will blow up past infinity. If y is too small, it will cause the axis to go to negative infinity somewhere. And the solution is the equation is complicated enough that unlikely you will have an analytic solution. You need to solve it numerically. And what we want to find is a regular solution. Obviously, blowing up is not an option, but the boundary condition to find a suitable solution is y need to go to 0, at x goes to infinity. Right? I want to impose that boundary condition, right? And by knowing this analytic property, then one obvious numerical method you can do is what we call the bracket method. So you choose one. If it blow up at the positive infinity, then you reduce it, or you either reduce it by a factor or whatever, or reduce it by half, and then if it reduces a certain amount, and then it blow up the other way, then you increase it, you decrease, increase, decrease, increase. So at the initial point, so somewhere along the line, you find out that for a certain particular value, it will go to a large x value before it goes to either one infinity at one way or the other, right? Obviously, with finite precision, I mean, even you use double precision, then you only have 16 digits, and sooner or later that it will go to infinity one way or the other. But if you use a high enough precision, for many cases, that equation will give you a nice solution up to a large enough x that is almost goes to 0 before it eventually goes to become singular at one way or the other. Right? So that there's some particular use for unknown equation. So whatever equation you try to do the look at the equation and analyze it to see what you should expect. And sometimes from this analysis, you can figure out what numerical method to use to solve it. And that is actually important because it depends on your boundary conditions. For this, the solutions look nice enough, regular enough for some even more complicated equation. But different initial conditions, different y value, it might actually get different property, totally different mathematical property or mathematical form in your solution. Okay, so these are just some general idea for deal with a nonlinear equation. And the third idea, of course, when you have an unknown equation that are not familiar, one first way you can do is look up a math handbook and see if it match some of the type of nonlinearity that for your equation. And that sometimes if you match certain type, you can reduce the complexity of your ODE and make it easier to solve. And that is also important because even if you reduce the order of your equation, that the numerical method to solve it will becomes easier. Okay, so now those are some general idea to deal with nonlinear equation. Other than that, not a whole lot to this general rule to talk about. Now for particular form, your textbook have 2 examples, but that is just, again, just 2 out of many different particular form, right? Because nonlinearity is too general. You can not becomes nonlinear in many different ways, right? So just saying that the nonlinear is not enough, right? Your textbook example, particular example, not difficult. So the first one is this Bernoulli equation. So you have a y prime equals to c y q y to a certain n power, and y x. This is power, not derivative. Okay. Then for this choice, for this form of equation, the method to solve it is to do this change of variable. So u is y to the 1 minus n power. And we'll see what that will change. So if u is like that, you obviously want to change it. This is equal to c. Oh no, this is not c. Y prime equals that. This is the equation. Y prime equals that. Okay, so to do a derivative, obviously either express y as a function of u and do that, or see if you just take a direct derivative, what happens? U prime is 1 minus n y to the 1 minus n minus 1 is minus n y prime. Right. And see what happened. And what you can do is multiply y to the minus n to the first equation, y to the minus n power y prime equals to p y 1 minus n plus q. Right? Let's change this to this first. Now you can use that. Y to the minus n power y prime is u prime divided by 1 minus n. This is u prime divided by 1 minus n. Now this y, the 1 minus n power is just u. Okay. Now this equation is linear in U, and first order linear equation in U, you know how to solve it, right? We have the general formula, we talk about that, general formula for first order ODE, first order linear ODE, we have the formula. It's okay, so that's just a very simple example, simple type of example. Of course, this is one particular type and out of infinite possibility. So obviously you won't encounter this equation that often, right? Because not all physical situation is describable by this equation, right? And now the next equation is a Riccati equation. The difference is that it has an inhomogeneous term that doesn't depend on y, and that makes it difficult to solve. y prime equals to p x y square and plus q x y plus this R function, which is non-zero, and then doesn't depend on y. Okay, so you have this type, and so it's simpler in the sense that it's not a genuine n, it's the square. This for the power of nonlinearity, but still because of the R that make it difficult to find solution. And the method is that there's no general method. It's just just in case you find one solution. In case you find one solution, you can y sub 0 is your solution. If y sub 0 satisfies this one, then you can use it to find another solution. And you might ask the question: you already have the solution. Why do you need to find another one? This is first order, right? So you have one solution already. So for linear equation, that's all it is, right? Just find one solution. But for nonlinear equation, that's not the case, because if you change to the other solution, find another solution, they will not most likely will not satisfy the same boundary condition or initial condition. You want to find another solution, or this solution might not satisfy your boundary condition, and you find another one that might satisfy your boundary condition. Okay, and so if this one might be easier solution for this one, and then it doesn't satisfy the boundary condition, then you use this method to find another equation, and hopefully that one will satisfy the boundary condition. Okay, so that's what it is. And now with this y sub 0, and what you want is define, again, change a variable. So y equals to this y sub 0 plus u. For linear equation, that doesn't seem to make sense. This is a solution. This already satisfied, and then add another one. You try to find this as then supposedly both of this u and y will be a solution, but not for nonlinear equation, like what we talk about. So this is a solution, and you want this solution. Obviously, u will not be a solution for this equation because of the nonlinearity. But you require y to satisfy this one. Right? So you will need a equation for u, and hopefully the equation for u is easier. Okay, and I substitute this into here. Y prime is y0 prime plus u prime, right? And so that's the left-hand side. The right-hand side becomes p, and then y squared becomes y0 squared plus u y0 u plus u squared, right here. And then plus q y0 plus u, and plus r. Right? Then now you can group all the term depends on y sub 0. So y sub 0 prime, you have a py sub 0 square, and then you have this depends both on y sub 0 and u, but then just the y sub 0 is this one, qy sub 0, and then you have our term also. But we already require that y sub 0 is a solution. So py sub 0 square plus qy sub 0 plus r is equals to y. I mean, this y sub 0 prime equals to this py sub 0 square plus qy sub 0 plus r, right? We already require that. We can cancel all this, cancel this with this and this and that, right? So what is left is u prime equals to q p y sub 0 u That's u squared plus u. Okay, now you recognize this is this of this form, the Bernoulli equation form, right? Because you have a linear term just like that, and you have a I mean, both this combined to a linear term. This both are linear, combined to a linear term, and then you have a q y n y to the power n. Now is p y squared. This Bernoulli equation with the setting n is to 2. Okay, so now you can follow this method to solve it. And so that the trick is this addition, because the difficulty of this equation is that you have an inhomogeneous term. So you find one way to get rid of that, then you have a simple equation. And the way to get rid of that is if you have an equation, or you can guess a solution that satisfies this equation, but might not satisfy the boundary condition, then you can use this equation, this solution, to get rid of the inhomogeneous term and make the equation simpler. Okay, then that's the idea. And sometimes I can generalize with other equations also. If you have a term that is unfavorable, but you have found another solution that satisfies the equation, you can use that this subtraction method to get rid of that term. Right? All right, that is the second example. And I mean, there are some other examples also, especially 7.8.2, but that again is too particular. You can follow that and change the form of the equation to a linear equation. And again, it's just an example of many possibilities. So we probably don't need to get an example. Okay, all right.